sorry about that. That should be fixed now. Let's transition back into there. Sorry, that should be fixed now. So only missed a couple of seconds here. Again, we're going to wrap up with heaps, binary heaps, and we're going to tail end everything with Heapsort, which is something that you implemented yesterday using heaps. Okay. So heaps, the motivation here is that binary search trees are not necessarily balanced, right? We've seen now examples. For example, you could go ahead and put in, 50, 60, 70, 80, right? ... And you could have a depth here, which is going to be order logarithmic. In other words, that is exactly what a regular old linked list is. And so putting stuff in, searching for stuff, anything that's index-based is now going to be extremely inefficient. It's just going to be linear, right? So one way that you can solve this is through balanced binary search trees, which goes beyond the scope of this course. But just as a quick example here, suppose that you do have a small tree that is unbalanced, right? Now what you can do is you can rename, or you can rebalance it by putting a little hill under here, right? And then what you do is you take the C right here, and then you pull it over the hill, right? That brings up B to the top of the hill and C down here to the bottom of the hill. Come on. No. Same problem. Anyway, you remember the image here that you would pull it up and over, and you would end up having A, B, and C, and thus rebalancing the tree. Okay. So unfortunately, yep, it's restarting. Yay, wonderful. Okay. Hopefully that'll come back. But in any case, that's our motivation. There are plenty of balanced binary search trees out there that go beyond, again, beyond the scope of this course. You have AVL trees, 2-3 trees, red-black trees, a whole bunch of different implementations. Again, they all work efficiently by rebalancing the nodes. We're not going to go that far, though. Today, we're simply going to go as far as a heap. A heap is a binary tree data structure that has the following properties. Right? So it is full. Right? At every level, all children are present, except possibly the last level, right? But the last level will be full to the left. Okay? In other words, there are not going to be any gaps in this thing. It is going to be a full contiguous binary tree, not a binary search tree, but a binary tree. The second property is that it satisfies the heap property. The key in every node is less than both of its children. That is in contrast to a binary search tree in which you've got a key, and then in the left child that's less than the key, and in the right child it's greater than the key. So without my tablet here, let's go ahead and open up some images instead. Here is my first heap. Where is it? There we go, min heap. Right. Now this one is referred to as a min heap because it follows that min heap property, that the key in any level, say for example, let's look at the root here, 1. It's less than both of its children, 5 and 30 here. If you take any other key, 55, it is less than both of its children, 72 and 77, right? So it is not a binary search tree. So one drawback to this, or one cost to using a heap as a data structure instead of a binary search tree, is that you lose all the generality, right? You can no longer search based on, well, I need to go left or right. If you want to search for 65, say, you would need to do a full pre-order, post-order, in-order traversal to find it, or a BFS, right? And so you do lose out on that potential for generalization. But what you do gain are a couple of things, right? So first of all, that fullness property. That fullness my first observation is that the fullness property guarantees guarantees that the depth is order log n. Right. So in other words, something that we were not able to achieve with the generic binary search tree, we now have this guarantee because it is full. And note here that it is full. Every single level, every single node is present except for the last level, and then we've got it's full to the left. Right? That guarantees that if I have an operation that is proportional to the depth, that it's going to be extremely efficient, logarithmic, just like binary search. Okay? The second observation, I'll ask you, what if I want to try to find a very special node in this? That very special node would be, say, the minimum. Yeah, it's just it's at the first one being the root, right? The minimum is always going to be at the root. You restarted. Let me go ahead and charge you up a little bit there. Maybe it'll come back. I can afford battery on my laptop here, but not forever. So let's see how far this goes. So my other observation is that the minimum element is always at the root. In other words, it's easy to find. This suggests that we can use this data structure for two basic operations. So the basic operations will be retrieve and remove the min element and put stuff in, add an element. Right? So we're going to have to develop those two algorithms here now. Okay? So retrieve and remove the minimum element, how would we go about doing that? Well, first of all, it's already there, right? We can go ahead and take that and put it over here to the side so that we can actually return it. But that means that we've left a gap. If we're going to take this out, we've left a gap. What's one strategy that we could follow to fill in that gap? Yeah. So that one's gone, right? I could promote one of its children. Right? Would it be more appropriate to promote 5 or 30 up to the root here? 5 because I want it to be a min heap, right? So 5 is right here. Okay, that's my best 5. Right? There we go. There we go. Right? Then now that leaves a gap right here. So which one do I put up now? 50, right? Why 50? It's going to be the minimum, right? And that leaves a gap right here. So which one do I promote up? 53. But now we've run out of children, right? So we've run out of children. We can't promote anything up. 53 is gone. We have a gap. The fullness property is no longer satisfied here. Okay, fine. Undo, 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 undo. All right. 1 is still gone, right? We've eliminated it because we want to retrieve and return and remove the minimum element. Instead of trying to satisfy, this heap property first, let's try to satisfy the fullness property. What among all these nodes here, what could I take and promote it all the way to the top to ensure that the tree is still full? 63. What happens when I put 63 up here, though? Right? It's not a min heap, right? The fullness property is satisfied. This one is now gone, right? But the fullness property is no longer satisfied. Or the fullness property is satisfied, but the min heap property is not satisfied. Now what you can do is, like we just did, swap with its minimum child. So 5 and 63 will end up getting swapped. 63 is now right here. Imagine that it's right here, right? And we end up swapping with that and 50. So 63 comes down here now. We end up swapping that with its child, and 63 ends up 63. There we go. That's my best 63 on a touchpad instead of a pencil over here. And the fullness property and the min heap property are now satisfied. Okay. All right. Sorry. Grade school drawings. That's the best tool we have right here. Do we have a different tool? What about this thing? What does this do? Oh, hey, there, that's freehand. That's a little bit better. Okay. All right, there we go. All right, so the idea behind retrieving and removing the minimum element is save off the root element, right, for a return value, right? Then promote the last node to the root node, and then finally heapify, fix the heap, by swapping with the minimum child until the heap property is satisfied. Right? Now, how complex is that going to be? If I have to swap all the way down, that's going to be proportional to the depth, right? And the depth has a guarantee of log n. Right? So the number, the complexity, the number of swaps slash comparisons is proportional to the depth. And because we have a guarantee, it's going to be order log n. There we go. Excellent. Now what about adding an element? Say I wanted to add, I don't know, 20. Should I start at the root here? Should I say 20? Okay, well, 20, no, I can't put that, I can't replace 1 because 1 is the minimum it has to be there. So do I go left or do I go right? Well, you know immediately by looking at the entire full picture, because it's all there for you, that I should go left. And the next place that I would need to insert something is down here. Right? We don't have that luxury just by looking at the root element, do we? So let's go ahead and magically jump to the end and put 20 right here. Right. Yeah, it satisfies the fullness property though, right? So we've got half of the equation. The fullness property is satisfied, but the heap property is not satisfied. So what do we do now? Same exact thing, but instead of going top down swapping, we go bottom up to swap. So 20 and 53, those get swapped. 20 is right here now. 20 and 50, those are out of order, so those get swapped. Where does 20 end up? Right here. 50 has been pushed down to 53, and 53 is now down over here. Okay? So from that perspective, again, it is going to be, as long as we have access to that last element, then it's going to be efficient, right? You add the new node at the end of the heap, right? The lowest possible level all the way to the left, right? Then you heapify upward, swapping with the parent until the heap property is satisfied, right? Now, if we have access to the last element, to the last position, I should say, then the adding is order 1. Right. Why? Because we're just creating a new node, making a reference to its parent, making a reference to the child, etc. And then heapifying is still order D. Order D, which we have a guarantee on that, remember, that it's going to be order log n. Okay? Heapifying. Yeah, the spell checker is telling me that that's not a word, but that's the word that we use. Right? We make up words all the time in computer science. Every discipline does stuff like that. They just make a new word for it. Okay? So these are the two basic operations. Heaps are not general purpose data structures. They are restricted access data structures. Where have we heard that term before? Stacks and queues. Right? Stacks and queues were only efficient because you restricted how you could use them. You could work at one end or the other end or both, but you couldn't arbitrarily go to the middle and do whatever you wanted, right? If you did, then of course it would be inefficient. Likewise, with a heap, if you wanted a general purpose search algorithm to find 65 or something like that, then you are back to square one, order n, because you're going to have to do a pre-order, post-order, or in-order traversal, right? It only is efficient if you restrict access to these two operations. Retrieve and remove the minimum element, or add an element. But it is extremely useful still, right? One application of heaps is going to be heaps are on efficient priority queue implementation. Do we remember queues? Right? First in, first out. It's a line, but a priority queue is different because you don't just stand in line and wait for your turn. Some people get in the line and they get to jump ahead, right? Because they have the highest priority. Some people have 0 priority and they're put at the back of the line. Some people have, intermediate priority, so they get to jump, but not everybody in front of them. So you have a priority queue where go ahead and put whatever you want in, and it's going to be efficient, right? You add an element, go ahead. But when you retrieve an element, you always pull out the minimum, the thing with the highest priority. And that immediately gives you an algorithm for sorting as well, because if you put stuff in and you take stuff out, the order that it comes out is not FIFO order, it is sorted order. And we're going to take a look at that here in a second. Before we do that, though, let's see where we are in our charge. 15, all right. Let's see if we can get some pictures up here, finally. Bear with me. Okay. Yeah. Did I shut down QuickTime? Yep. 1 second. This is why tablets need 2 USB-C ports to charge and then to... There we go. All right. We're back up. Good. All right. So let me go ahead and show you a picture, that same picture over there of a min heap. There we go. Okay. How could we efficiently implement this? Now, you could go the route of a binary search tree the way we did it. You could create a tree node that has a reference to the parent, left, and right. And then you could reuse that, and you could have a tree data structure representation of this. The problem comes in with that assumption that I made over here, right? If we have access to the last position, then you can just simply add it. How can I get access to the last position? In other words, if I'm going to insert 20, it's going to have to be the left child of 53. How could I immediately jump for free to that location if I just have a tree data structure? I can't, right? That sounds more like random access to me, right? Jumping to a particular memory location. So if we have a tree data structure, we have to start at the root. Now, there is, if you figure out the math, that if you start here, where is the next position? Is it in the left subtree or is it in the right subtree? Now again, as humans, we can immediately see that it's in the left subtree, but that's because we can see the whole picture at once. A computer wouldn't be able to do that. A program wouldn't be able to do that. A program would need to be able to decide, oh, well, should I go left because it's over there, or should I go right because it's over there because this entire thing is full? Luckily, it's pretty easy math to do that. All you need is the series. You remember the series? The summation of I equals 0 up to, say, d of 2 to the I is going to be 2 to the d plus 1 minus 1. You can use that to determine, and then the total number of nodes, n, to determine whether or not this subtree is full or this subtree is full, or vice versa, which one is empty, right? That tells you, oh, okay, well, it's in this left subtree that I need to go. Now, when I'm there, I redo the math and say, okay, well, it's in the left subtree that I need to go. When I do the math here, I see that, well, here. When I do the math here, I see that this left subtree is completely full. This right subtree is not, and so I need to go to the right subtree. And I finally find out where I need to go next. It's still going to be order D to do that math. But I'm going to show you an even easier way to do this. Now, do you remember one of the other traversal strategies? Not pre-order, not post-order, not in-order traversal, but the traversal strategy that went top to bottom, left to right. Do you remember what that was called? BFS, right? Did you say DFS? Or, oh, okay, sorry. I heard B. I heard D because DFS is depth first search. But this is breadth first search. Why is it breadth first search? Because you search things that are 0 distance away, then things that are 1 distance away, then 2 distance away, 3 distance away, and then finally 4 distance away. Ignore my fingers, I think it was off. All right. Let me go ahead and write that down. 1, 5, 30, 50, 55, 40, 80. Let's go a couple more here. 60, 53, 72, dot, dot, dot. Right. Now, what if I associated with that an array? I'm going to start at index 1. I'm going to burn index 0 here, and we'll see why in a second. 2, 3, 4, 5, 6, 7, 8, 9, 10, dot, dot, dot. Okay. Now, how does this help me? Well, first of all, it matches this BFS perfectly, right? Everything is contiguous, right? And it's all top to bottom, left to right. Not only that, but if I were in a tree here, one thing that I would want to do is go to the left child. The other thing I would want to do is go to the right child. Now, if this were a tree node, of course, I would just have a reference immediately to its left child and a reference immediately to its right child. But it's not a tree node. It's an array. So how do I get to 1's left child? It's right next door. How do I get to 1's right child? It's right next door to its left child. Okay? Well, that works for the first one. Let's take another arbitrary one, like 50 here. 50. Oh, did I miss it? 30. Oh, okay. There we go. I already had 5 right there. Okay. Sorry. Is this correct? 5, 30, 50, 55. Yeah, there we go. All right. So let's go with 50 here. Where is its left child? Its left child is 60, so I would have to jump to 8. And right next door to it is its right child. Left child and right child right there. Okay. So we can see a pattern emerge. If I've got a node at index I, where is its left child? At 2i. Where's its right child? Right next door at 2i plus 1. Right? Now this is why I burned 0, because otherwise it would be subtracting everything off, right? -1, -1 everywhere. In fact, it wouldn't be -1, it would be -1 on I, which is even less clean. And so that's why I burned the 0 index there. Okay? What about the parent? Well, let's reverse this. If I go from I to 2i, well, then to reverse it would be I divided by 2. That works for the left child. But what about the right child? 9 divided by 2 is 4.5. Is that an index that you've ever heard of? No. Truncate it or take the floor. Right? Cool. So I divided by 2, truncate or floor. Right? Because there is no math truncate. Right? Excellent. So we've got an efficient way to store this and an efficient way to jump around to the left child, right child, and back up to the parent. Right? By the way, is that sorted? No, not at all. It's heapified, right? It is in a heap data structure, but it is certainly not sorted. So how does it work to pull things out? Again, you pull it out and you save it off so that you can return it. That leaves a gap, though. Right? That leaves a gap in both of these things. What do we replace it with? Well, that means that we have to go jump to the end to get 63 and promote it up here temporarily, and then heapify it down. Right? Now do we have free access? Remember that caveat here? If we have access to the last position, then we can immediately jump there for free. What's the last position here? If I were to write the rest of this out, what index would it be at? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 things. So where's the next thing? At index 18. All you have to do is keep track of the size, the number of elements in there, and you can immediately jump to that index for free. And that's why it's such a nice, elegant implementation of a heap just to use a regular old array. Now you might be asking yourself, well, wait a second. Why didn't we do that in the first place with a binary search tree? And good question. Let's go back to our binary search tree. There we go. I don't like that one. That wasn't a binary search tree anyway. It was a binary tree. Here's my BST. Right? Now think about this in an array. What does it look like? 50, 40, 60, 20, 45. Fine so far. But what about 60's left child here? What's going to end up having being there? Nothing. A gap. Right? 90. Right? 10. 24. Another gap. 49. Ooh. 2 gaps. Right? Then 80. 95. Dot, dot, dot. 2, 15. A gap. 28. 48, and now how many gaps? 1, 2, 3, 4 gaps. 75, 85, 2 more gaps, and then another gap for right here. Actually, 2 gaps, right? And then 12, and then dot, dot, dot. In other words, lots and lots of gaps. This is a small tree, but you can imagine if you had, say, a depth 10 tree, a depth 20 tree. Guess how many gaps there are now? An exponential number of gaps, right? In other words, to store it in an array configuration means that you're going to have to be storing a lot of empty spaces and wasting a lot of memory, wasting an exponential amount of memory potentially, right? So no, it is not an efficient implementation of a binary search tree or a binary tree in general, but it is an efficient implementation of a heap because you have this fullness guarantee. You will have no gaps at all. Excellent. That leads us to another application. In fact, before we look at the application here, let me show you how Java does a heap. A heap in Java is just simply a priority queue, as we hinted at here. So priority queue for what? Elements of type T. I'll call it H for heap. In fact, I'll name it heap. Is equal to new priority queue. There we go. And what I'm going to do, here's the outline. Hopefully you did it. For each element X in the list, remove X from the list and add it to the heap. Here's an easy way of doing that. Heap.add all list. Now I didn't remove anything from the list, so I'll go ahead and go list.clear. There we go. Right? I'm getting around writing my own loop here that we hinted at. Why? Because if you look at the code, guess what they do? They do the loop for you. All right. Nice little convenience functions all over the place here. Okay. And now what I want to do is I want to system.out.println. Let's print the heap. Okay. What is the? That's not 99. That was supposed to be 9. There we go. So 9, 4, 6, 2, 7, 8, 1, 3, 4. When I put all those things into the heap, does it look sorted to you? Is that sorted? No. Right? What does it look like when you depict it as a binary tree, though, as a heap binary tree? I don't want to lose track of it, so let me just go ahead and write it out, and then I'll show you really quick. 3, 2, 4, 7, 8, 6, 9, and 5. So what I did is I wrote those out as a tree. That's a min heap, right? It was actually storing them as an array. And I can show that to you too, right? let's take a look at the priority queue. How does it actually store the stuff? In an object array. In fact, it tells you right here. Children of the queue are 2n plus 1. Instead of, they used n instead of I. And then 2 and q. The priority queue is or the 2 times n plus 1. And then this is 2n plus 2. And so they're not burning that 0, right? So their math is a little bit different because we burned that first one, right? We ignored that that index 0 there. They're not ignoring the index. They're just subtracting 1 off of each one of these ones or something, right? So that's why their math is a little bit different. Otherwise, they're storing things as an array. You can use a comparator for the priority, ... blah, 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 right? In fact, I also showed the class earlier was, note this restriction of at least one, but whatever. Okay. Oops, find, there we go. Right. How do they compute the parent? How do they compute the children? Right? It's multiplication by 2 plus minus 1, or division by 2 plus minus 1. Have we seen that before? That greater than, greater than, greater than? If not, let's discuss it. Right. So, first of all, if I have 3, 1, 4, 5, 9, if I've got 31.459 and I multiply it by 10, how easy is it to do that? Should be pretty easy. What do? You what? You move the decimal over. You float the point over. Floating point numbers, right? If you want to divide by 10, what do? You float it that way, right? Now, we don't have, base 10 in computers. Instead, we have base 2. Base 2. So what does it look like when you float things over? Here's 7, 1, 1, 1. Right? What happens when you float the decimal point over here? Right? And then, of course, truncate this. You have 1, 1. In binary, what is that? 3. In other words, 7 divided by 2, truncated. Right? What does it look like to take 7 and multiply it? 1, 1, 1. What if you move the decimal point, the implicit decimal point over here by 1? And now there's a 0 here. Right? So this is 1, 1. Do you know what that is? 1, 2, in base 10, 4 and 8. 8 plus 4 plus 1 is 14. 7 times 2 is 14. So, shifting this over one way or the other is a convenient way of multiplying by 10, or if you're in base 2, it's a convenient way of multiplying by, or dividing by 2, or multiplying by 2. Right? And in code, you can do that one of several ways, right? I is equal to I times 2. Right? That's the really long-hand way of doing it. A shorter hand way of doing this is multiply equals 2. Right? You're doubling it. Or an even better way of doing this is to shift it over by 1 bit. Right? And that's what this is doing right here. You're shifting it over. You're multiplying by 2, or division would be the other way. I divided by 2. I divided equals 2. I shift over by 1 position, by one bit. You might have to set this equal, of course, if you want to retain it. Otherwise, it's just divided by 2, but not doing anything with the result. Right? The difference here with Java is I believe that this is a cyclic shift. So what happens to the bit is it goes on to the other side. Right? So don't ask me why they're doing a cyclic shift there. I'd have to figure out the math for myself. But nice little digression there. Okay. All right. Let's take care of the last part here. Right? While the heap is not empty, remove the minimum element and add it to the list. So while the heap is not empty, I've already cleared the list, so list.add heap.pull. Hopefully this is what you did in your lab yesterday. Right? And when you run this, now what comes out of that is a sorted list. We call that thing Heapsort. Let's analyze it, because this is awesome code, right? This let's look at pseudocode for this. Right? Hopefully this is still going. So here's Heapsort. My input for this is going to be a collection A of elements. Right? And my output will be A sorted. Okay? What does the pseudocode look like? All you have to do is establish a min heap. And then for each A in A, h.add A. Just one for loop. Put stuff in. Put stuff in. Now all you have to do is while h is not empty, I will go ahead and set a sub I to be h.getMin. Right? And I++ here. Initialize I to 1. There we go. There. And that's it. That's all. Put stuff in, take stuff out. Do you remember one of the themes to this course is a quote by Eric S. Raymond that smart data structures and dumb code are a lot better than the other way around? Dumb code. Put stuff in, take stuff out. But what have you achieved here? Sorting, right? Some things that we've looked at, complex, clever algorithms up to this point. Selection sort, insertion sort. Right? Selection sort's kind of dumb and inefficient, but insertion sort is a little bit more clever because it's adaptive, right? It doesn't need to compare to everything in every iteration. Quicksort is even more clever because it's a divide and conquer strategy, and it's even more efficient. Merge sort is cleverer still because it zippers things up, right? Those are all clever sorting algorithms. Clever code, no data structure. Here, we've got smart data structure, dumb code, right? Now, it's all for naught if it's not efficient. So let's analyze it. So what about the put stuff in phase? Stuff in phase. ... So I'm going to go ahead and label each iteration. Iteration 1, 2, 3, 4, ... The last iteration we do is n. Why? Because for each element A in A, we put the first one in, second one in, third one in, ... the last one in. Okay? I'm also going to keep track of the size of the heap. Initially, the size is 0, right? Because there's nothing in the heap. After you put the first element in the heap, the size is now 1. And you put the second one in, the size is now 2, 3, ... n minus 1. On the last iteration, you've put n minus 1 elements into the heap, and you put the last element in there. Right? So the number of comparisons for each one of these things is going to be log of n. Remember, this is n, the size of the heap. So log of 0, which is undefined. We'll just say that's 0 because we don't do any... how do you insert into an empty tree? You create a brand new root node and you're done. No comparisons at all. Otherwise, log of 1, log of 2, log of 3, ... log of n minus 1. Now we are off by 1 here. Don't worry about it. This would end up being 0 comparisons, but we actually have 1 comparison. So add 1 to each one of these things if you really want to be pedantic about it. Don't worry about it. Add these up. How can I sum all of these? All right. Log of 1 plus log of 2 plus log of 3 plus ... plus log of n minus 1. Do you have your log identities off the top of your head? Log of A plus log of B. Log of, say what? Multiplication, A times B. Apply that to all of them. Right? Okay. Well, let's not jump all the way there, but it will be factorial. All right, then, sorry. Multiplication, ... multiplication, n minus 1. Right? So that's equal to log of n minus 1 factorial. You were right there. I don't like dealing with that minus 1. So let's make it bigger, because it's big O analysis, right? We make it bigger, it's still going to be big O. So less than or equal to log of n factorial. Okay. How can I make that even bigger? Because factorial, you can pull out something called Stirling's formula, right? Stirling's formula, and get a continuous version of the gamma function being factorial. I don't want to do that because that's all calc. Forget about that. Let's just do algebra. How can I make it even bigger? Log of n to the n. Why is that true? N is bigger than 1, right? N is bigger than 2. N is bigger than 3. Right? And I can certainly add another n over here for all positive n's. Right? So this is true. Now apply another log identity. What can you do with that exponent? N log n. Right? In other words, it is order n log n. So not only do we have really, really dumb code, smart data structure, but we also have guaranteed efficiency, at least in that first phase right there. But guess what the second phase, what the analysis looks like there? It's the exact same thing, but in reverse. As you take stuff out, the size of the array goes, or the size of the heap goes down, right? And so you have this times 2, but guess what happens to that 2 out front? It gets ignored. And we still have order and log n. Smart data structures and dumb code are a lot better than the other way around. Right? Thank you, Eric S. Raymond. He's a reprehensible person for other reasons, but don't worry about that. Right. He's kind of persona non grata, I think, now. But anyway, he had some good catchy sayings in his book, Cathedral and the Bazaar, if you want to check it out. Right? I don't want to get into it. He's pretty misogynistic in his other writings. Right. All right. Any questions? Then we have a choice. I guess we've got plenty of time. The morning section, they wanted to see JPA on Tuesday and then have a course wrap up on Thursday. Do we want to see JPA as well in here, or do we want to see something? Remember JPA, what does that look like? It looks like, where's my JPA demo? Here. I don't like writing JDBC. Now that I've learned how to do it, I'm going to learn how not to do it. So I'm going to annotate my classes so that this address class is associated with the table called address in my database. This address ID is a field in my database is a column in my database called address ID. It's an entity, so you are I'm talking to JPA now. You go ahead and write all the JDBC code for me, auto-generate it all, so that it loads this stuff up automatically. Right? What's the ID? What's the primary key? Well, it's this one. I annotate it to say ID. I generate its value, and I let the framework take care of everything for me. I want to load up all the addresses. All I have to do is this. Right? I don't even know if this will run. I don't think I've set this up. All right, am I doing anything? Oh, because I'm not. No, I'm not doing anything. Connection pool size, log persistence unit. Well, maybe I could get it to work if I put in the right password. No, that's Maven. Sorry. Where's the? Where is my persistence XML file? Oh no. Okay, it's definitely not set up correctly. Did this ever work? There it is. Resources, meta inf. There we go. All right. Well, it's still going. I don't know why it's going still, but probably other people have reported problems with the database today. No, that's the correct password. It's just taking forever, maybe. All right. Well, we'll let it sit there. Do we want to see the same thing, or do we want to see something else, or do we want to? We could do our course wrap up on Tuesday and then call it off on Thursday as well. I'll let the folks in here decide, since you guys are the ones that show up in person. It won't affect the online folks at all. What do you want? CJPA or not? Oh, you want to see it? All right. We'll go ahead. There. Finally it died. Broken pipe. Why were you broken? Up there. I'm able to get the communications link failure now. So, yep. The students out there that might be watching this and haven't seen that, then you are not crazy. I've already put in a ticket, by the way. If you have been experiencing this, they should be taking a look at it, but I have no idea if they're going to get what their resolution is going to be. I'll check my email after we're done here. So we'll go ahead and hold a class on both of those days. Remember, do fill out the course evaluation at some point. You've received emails about that? Yes? Okay. Fill that out, and we've got assignment 7, 8, which is written, and the design document. Once those are in, once those are done, you're done with the course. So, any questions? All right.